Hey guys, welcome to the Chapter 12 study guide. Okay, so you're going to have a couple of questions like this asking you to identify the type of bond, and I don't mean James. Okay, anyway, so the type of bond being formed, well, this one's ionic. And the reason this one's ionic is because chlorine is actually stealing this electron. And whenever something is being stolen, in this case the something being the electron, when the electron is being stolen, they're not sharing, therefore it is an ionic bond, which kind of answers the next question. What are the electrons doing? Well, the electron is leaving sodium and it's going to chlorine because chlorine's stealing it. And how would you describe the bond in terms of electronegativity? Remember, electronegativity, we're looking at the differences. And the greater the difference in electronegativity tells you something about the bond. So in this bond, I would say there is a high difference in terms, I have my bad pen, sorry. A high difference in terms of electronegativity. And that's partly A, because, things are being stolen, and 2, that's the definition of an ionic bond. Taking a look at this picture, well, this one, the type of bond is a covalent bond. I changed pens, can you tell? Okay, so the covalent bond, we know it's covalent because the electrons are being shared. And by definition, covalent means to share. Co as a prefix actually means to share. So this is a covalent bond. And I just went and answered this next one. What are the electrons doing? Well, they're sharing. And how would I describe each of these bonds in terms of electronegativity? Well, in terms, I would say, between hydrogen and carbon, this is a slightly polar bond. And so there is a slight, IGHT, slight difference in electronegativity. Each one of these bonds, each one is slightly polar. Now, is the entire molecule polar? Nope. The entire molecule is not polar because if you remember, this is a tetrahedral shape. And there is a symmetry, I'll write it out, hedral. There's a symmetry there, and around this entire molecule, no one end of the molecule is being greedy. And so we could say that each of these dipoles gets canceled out, and the molecule itself is non-polar, still covalent. Okay, the easiest way to start this particular problem is by writing the electron configuration for the phosphorus atom. All right, let's find phosphorus. There you are. Oh, there's my pen. Okay, there's phosphorus. So I'm going to go ahead and start with neon because that's the shorthand for phosphorus. So neon. And then let's see, 1, 2, third energy levels, so 3s2. Then we go all the way over here to 3p3. Now, when phosphorus becomes an ion, what does that mean for phosphorus? Does phosphorus gain electrons or does it lose electrons? Well, phosphorus gains electrons. And how many does it gain? Well, I know the charge on phosphorus is -3, so it gains 3 electrons. I could write it as neon, and then 3s2, and then 3p. It gained 3 electrons, so this 3 becomes 3p6. But if I look at the periodic table, adding 6 more electrons to this guy, 1, 2, 3, that means phosphorus has the exact same electron configuration, well, the phosphorus ion, I should say, has the exact same electron configuration as argon. Okay, now, taking a look at the ion sizes. Here I have the phosphorus atom. I'm going to change my color. There we go. That is the phosphorus atom. And look at the phosphorus ion. Whoa, man. That thing got huge. Oh, snap, I have the wrong pen. All right, one of these days I'm going to throw that bad pen away. But anyway. Okay, so there we are. There's the phosphorus ion. Man, that thing got big. Well, as a general rule, remember, anions are always larger than the atoms from which they came, and cations are always smaller. Why would this be? It has to do with the effective nuclear charge. This is the pull the electron feels from the nucleus. This phosphorus atom has a nuclear charge of 15 because there's 15 protons, and out here in the electrons and their little orbitals out here in different shapes and sizes, you have 15 electrons. But the ion also has 15 protons, but it has 18 electrons out here somewhere in their appropriate orbitals and shells and the whole thing. And you know, these 15 protons just cannot hold 18 electrons quite in the same way it can hold 15 electrons. So it gets bigger, which kind of makes sense. If you gain electrons, you get bigger. The cations, when you lose electrons, you get smaller. Okay, we're now looking for ions that are isoelectronic to the phosphorus ion. Reminding you that isoelectronic means they have the same electron configuration. Well, we'd already discovered that phosphorus ion happens to have the same electron configuration as argon. So any ion that has that configuration would qualify. So sulfur wants to be like argon. So that would work. Let's see. Oh, chlorine would. That would work. Oh, let's see. We could even go with silicon if you wanted to, even though it's a metalloid. But what about the cations? What cations would be isoelectronic? Well, these have to be ones that would lose an electron to look like argon. So that would be potassium would be one, and calcium would be another. All right, well, that's not too painful. Now we have to organize them from smallest to largest. If you recall, when you lose electrons, you become smaller. And the more you lose, the smaller you get. So calcium would definitely be the smallest. And it's going to be smaller than potassium. You could put argon here if you want, but argon is not at all, really not in any way, shape, or form an ion, so I'm going to skip it. Okay, so, gosh, I have way more than 4. We'll go with it. The more electrons you gain, the bigger you get. This guy gained the least. So chlorine, followed by sulfur, followed by phosphorus, and then, oops, I should put my little signs in here, and followed by silicon. And the only way you can compare these nicely, the ion sizes, is if they're isoelectronic. If they're not, it's way more difficult to compare the sizes, unless, of course, you're comparing them within the same group. Then that's not too hard. As you compare within each group, as you go down the periodic table, they're going to get larger no matter what. Okay, we have to organize these in terms of increasing polarity. So that means we want to go from nonpolar covalent to covalent to ionic, if that's available. I like to start on the 2 extremes. So out of all of these choices, which one is the least polar bond? Well, if you said FF, you are correct. That is the least polar. Identical twins share perfectly. There is no distortion of the electron cloud. But remember, when we look at bonds and polarity, we're looking at differences in electronegativity. And when they're exactly the same atom, there's no difference in electronegativity. So that's why we say they share perfectly. Now let's see if we can go to the other end of the spectrum. Let's see, those are both nonmetals and oh, look at this. That's a metal. Clearly this bond has to be ionic because I have lithium. It's way over here. So lithium and fluorine, lithium's a metal. It's got to be a cation. That one's ionic. I'm even going to rewrite it to make it look more like an ionic bond. And now I'm going to get rid of these. I don't want to see them anymore. All right, now where do we want to look next? These are all with fluorine, so it can't be that big of a deal. Well, let's see. Why don't we go with, they're all going to be with fluorine, carbon. We've got carbon, nitrogen, and oxygen. Okay, so out of those, who would have the smallest difference in electronegativity? Well, if you said the oxygen-fluorine bond has the smallest difference, you are correct. So, fluorine and fluorine would be less polar than oxygen and fluorine because their oxygen and fluorine are pretty similar. And then after that comes, nitrogen and fluorine. And then we have carbon and fluorine. The farther apart, the bigger the difference in electronegativity, the less well they share. So we need to describe what these pictures are trying to tell us. And I'm going to do that by looking at the top picture, and that is very clearly a polar molecule. It's polar because the atoms are not sharing well at all. And we can tell this because this electron cloud, this blue fuzzy area all the way around these two atoms, it's pretty distorted. It's not an even, smooth shape. And one side of this molecule has a partial negative charge, and the other side of the molecule has a partial positive charge. It ends up with two separate poles. And has two separate poles, that's what's going to make it polar. Now to take a look at the bottom picture, this one is extremely nonpolar. We know it's nonpolar because one, the atoms are sharing well, and we can tell they're sharing well because this electron cloud is not distorted. It's evenly distributed around those two atoms. And that's pretty much all you needed to do for these two problems. Or rather, these two pictures. So why is it that the trend in electronegativity is the same as that for ionization energy? Well, first off, let's identify what electronegativity is. And that's the ability of an atom to draw electrons to itself. And then ionization energy is the energy needed to take away an electron. Well, think of it this way. Once an atom, we'll say this is fluorine, goes through all that trouble of getting these electrons drawn in, it certainly is not going to let go. No way, no how. It's like seagulls in Nemo. They're sitting there going, mine, mine, you can't have it. Or in the words of one of my brilliant former students, the more you want something, the harder it is to take it away. I know that number 7, I have a different chemical here than I actually put on your study guide, but in retrospect, I think this one's better, so this is the one I'm going to go with. So phosphorus trifluoride. First, we have to figure out how many valence electrons this molecule has. So has. Phosphorus has 5 valence electrons. Fluorine, each one of these guys, I'm going to make those like that. Each one of these guys has 7 valence electrons, so that's 21. So this molecule has 26 valence electrons. This molecule phosphorus wants 8 valence electrons, and fluorine, each of these 3 wants 8. So that's 24. So this molecule wants 32 electrons. To figure out the number of bonds, I'm going to subtract these two numbers. So 32 minus 26 is 6 bonding electrons. Divide it by 2 because there's 2 electrons in a bond, so we end up with 3 bonds. Putting the less electronegative atom on the center, we end up with P. So I'm going to put a fluorine there, and a fluorine there, and a fluorine there, because they look evenly spaced. But then I have to make sure I have 26 electrons placed on this molecule, and I've only put 6. So there's 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, and 26. Good job. There's the Lewis structure. The electron geometry around this central atom. It's always about the central atom. Well, here we have 1 thing, 2, 3, and 4. So I have 3 bonds and 1 lone pair. So that's 4 things around the central atom. That means it's tetrahedral. The molecular geometry then around the central atom is whenever you have a lone pair and 3 bonds, the shape is always going to be trigonal, pyramidal. The bond angle. Well, our bond angle for a tetrahedron or a tetrahedral structure is 109.5 degrees. But this lone pair takes up so much space, it's going to kind of squeeze these bonds in a little bit. So whenever we have a lone pair, our bond angle will be less than 109.5 degrees. How many lone pairs are on the central atom? Well, that should be easy. There's 1 lone pair right there. And is this molecule polar or non-polar? To visualize this molecule in 3 dimensions can be rather difficult, but we have this huge area of an electron cloud created by these lone pairs, and then look, we have these huge area of negativity. This bond itself is polar. We have a partial negative here and a partial positive here, and that gets repeated. Partial negative, partial positive, partial negative, partial positive. And here, all this area is negative. So overall, there's not one side of this molecule that is more polar than the other. So I'm going to go with non-polar on this one. Okay, well, carbon tetrahydride. Yep, gonna have to have the formula again. CH4. Do you know the common name? Well, if you said methane, you're correct. So your Lewis structure, carbon, we have to figure out how many valence electrons this entire molecule has. Carbon has 4. Hydrogen, there's 4 atoms, and each one of those has 1. So this molecule has 8 electrons. What it wants to feel like it has, carbon wants to feel like it has 8. Hydrogen, each one of these wants to feel like it has 2. So it really wants to feel like it has 16 electrons. When I subtract these 2 numbers, I end up with 8 bonding electrons. Divide by 2 electrons in a bond, I end up with 4 bonds. Putting carbon in the central atom, C for carbon. Carbon in the center, 4 bonds coming off of that. And we now have the structure for methane. The electron geometry around the central atom, just like in the previous problem, it's tetrahedral. because there's 4 bonds around the central atom. And the molecular geometry, because there's no lone pairs, it is the same. It is tetrahedral. I just answered the next question. Oh, no, I didn't. It's 109.5 degrees. Tetrahedral's always 109.5. There's no lone pairs on the central atom. And the molecule is nonpolar. Even though each one of those carbon-hydrogen bonds is polar, each one of these bonds is a little polar. Being tetrahedral, there's symmetry to this molecule. There's not a single area on the molecule that's more polar than the other. So the molecule itself is nonpolar. Boron trifluoride. Here we go. Boron has, let's see, because we have to, probably should have a formula first, yeah. Boron trifluoride. There we go. All right. And has, let's squeeze that in here, has. How many valence electrons does this molecule have? Well, boron has 3 valence electrons. Fluorine, there's 3 of them. They each want 7, so that's 21. So this molecule has 24 electrons. What it wants, watch it, be careful, because remember, boron really only wants 6 electrons. Fluorine, well, there's 3 of them, and they each want 8, so that's 24. So this molecule wants 30 electrons. So I subtract these 2 numbers, and I end up with 6 bonding electrons. Divide by 2, that's 3 bonds. All right, boron with 3 bonds coming off of it. Now I have to make sure all these atoms are happy by putting all 24 electrons on the molecule. 2, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Oh, well, that's cool. And boron doesn't get any more because boron is quite happy the way it is. So, what is the electron geometry around the central atom? Boron only wanted 3. It's got 3. There's only 3 things, in this case 3 bonds around the central atom, so that shape is trigonoplanar. The molecular geometry, because there's no lone pairs, it is the same. It's trigonoplanar. The bond angle for a trigonoplanar molecule is 120 degrees. And I've already answered this one. There's no lone pairs on the central atom. Nope. And the molecule in this case is nonpolar. Even though this is partially negative, this is positive, that same pattern repeats. There's not a single area around this molecule, like I don't have a bunch of negatives on this side, a bunch of positives on this side. The molecule is symmetrical all the way around, so it is nonpolar. Ooh, sulfite ion. Sulfite ion, SO3 with a 2 negative charge. Sulfur, well, that one has 6 valence electrons. Oxygen, it has, well, we have 3 of them, and they each have 6 valence electrons. Don't forget, we have these 2 extra electrons on this molecule. So we have 18 plus those 2 plus 6. So this molecule has 26 valence electrons. But what does it want? Sulfur wants 8. Oxygen, all 3 of these guys want 8. So this molecule wants to feel as if it had 32 valence electrons. When I subtract this number and this number, I end up with 8 bonding electrons. Divide by 2, we get 4 bonds. Putting sulfur in the middle, 3 oxygens around it, but that's only 3 bonds. I'll put 1 more bond in. It doesn't matter where. So we have 26 electrons to place. 2, 4, 6, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Lastly, don't forget, because it's an ion, you need the brackets. Just a notational sort of thing. There's your Lewis structure. The electron geometry around the central atom. If you recall, we're going to treat a double bond for the geometry purposes as if it were a single. So I have 1 bond, 2 bonds, 3 bonds, so the geometry is trigonal, planar. And because there are no lone pairs, the molecular geometry is also trigonal planar. The bond angle is 120 degrees. I've already answered that one. Here we go, the last question. Sulfur tetrafluoride. Sulfur tetrafluoride, well, that would be SF4. Sulfur, in this case, has 6 valence electrons. There we go, that's a 6 really. And fluorine, there's 4 of them, 7 valence electrons, that's 28. So 28 and 6, we have 34 valence electrons. And this thing wants, well, sulfur wants 8. Fluorine, I've got 4 of them, and they all want 8. So that's 32 and 8. That's 40 electrons. Well, 40 minus 34, that's going to be 6. Wait a minute. This is one of those examples where it's just not going to work, isn't it? Well, let's put sulfur in the middle. We know there's going to be 4 fluorines. It's going to come off. I still have to place these 34 electrons on it, so let's give it a try. 2, 4, 6, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34 electrons on the central atom. The electron geometry around the central atom then, because there's 5 things. We've got 4 bonds and 1 lone pair, so it's trigonal bipyramidal. Because there's 1 lone pair on the central atom, the geometry on this one's called seesaw. Really, it really is. And the bond angle, well, if this is my axial atoms, which I can't touch, those are 180 degrees, then these are all going to be 120 degrees. And is this molecule polar or non-polar? I'm going to give you a chance to look at this entire molecule and see what you come up with. That's the last question on the study guide. Good luck on your test.